So the next speaker is Radek Piórkowski from University of Warsaw. He's a PhD student, and he will talk about, I guess, some structural understanding of two-dimensional vases. Please start.
Thank you for the introduction, Wojtek. In this presentation, I'd like to tell you about our new geometrical approach to pumping in two-dimensional vases. So this presentation is based on a work that I did with Wojtek Czerwiński, Sławek Lasota, Krzysztof Luding. Three of us are from the University of Warsaw, and Krzysztof works in Aachen. So what is the plan for this talk? First of all, I will present you a brief introduction to the most important concepts that we work with. Later, I will describe our pumping method in the greater detail. As an application of our method, I will show you how one may use it to prove a short-run property. And finally, I will tell you a few words about why we think it's interesting, why we even studied that, and what are our plans for the future. So there's no time to lose, so let's just jump straight to the introduction. In this section, I will tell you what is a two-vase. This probably most of you know, but I will show you how I will be drawing them on my slides as well. Also, I will tell you what I mean by pumping, and I will tell you how our pumping method relates to other pumping lemmas that you may have already seen. So, a two-vase. A two-vase is a 2D vector addition system with states. So let's just look at all those words that appear in the name of this model. First of all, it's closely related to the Petri nets, of course. So first of all, 2D vector, that is, the transitions of the system will be more or less 2D vectors, and I will be drawing them like this. The other keyword with states, and I will draw the states as the colorful dots like this. So for example, if I, can you see my pointer? My mouse pointer or not?
I don't see this.
Do you see it or not?
Ah, yes, we can see, yeah.
Okay, so maybe I will be using it to point to something. All right, so yeah, I will just draw those states as a colorful dots like this. Okay, so for example, the first transition is from the state P to the same state again, the other one as well, and the third one is from P to Q. So basically, what we have here, the set of transitions that go from some state to other states is a vase, and it only uses 2D vectors. All right, so I will try to avoid formalisms as much as it's possible, so I will only use those drawings in my slides. Finally, the word addition means that we may add those vectors one to another. So for example, if we start from some state here, we may add this vector that has a red initial state, and we may add vectors again and again. And by adding some sequences of vectors, we get a run of a two-vase. And the important thing, important rule here is that a run can never go below 0. And basically, this is all that I need to tell you how vase works. Now, there's an important problem concerning vases. It's a very hard problem. For example, that is the reachability problem. So given a 2 vars, is there a run from some configuration to some other one? And concerning this problem, for the arbitrary dimensions, there was some major recent progress done by my colleagues. Let's take a look at the history of the developments concerning the reachability for arbitrary vases. First of all, an XP space lower bound was shown. Then the problem was actually shown to be decidable. And recently, the gap of the complexity of this problem was very, I mean, it became much, much smaller than it used to be before. So yes, this is 2 vars. The next thing is pumping. So what I mean by pumping. The simplest case in finite automata is as follows. This is a property that states that if we have a run that is long enough, then actually some kind of repetition will occur inside it. And we might extract the part of this run and repeat it many, many times, or even delete it from the run. And what we get are valid runs again. So how does our pumping method relate to this simplest case of pumping? The first observation, the first easy observation to make here is that now repetitions of states are not enough. For example, if we have a run like this, and some states in this run repeat, for example, Q and Q here, then pumping is not possible here. So if we repeat this second time, we already broke the run, and it gets worse and worse if we progress with that. So we need something more. And generally in vases, pumping was not considered before. It was only possible in one-dimensional vase, which is also known as a one-counter net. And concerning higher dimensional systems, we had, and I think we still have, very little intuition what's going on there. So that was one of the things that motivated us to consider pumping in 2 dimensions. Our pumping lemma that we provide looks as follows, but maybe it's not that important to look at it very thoroughly. The intuition is that now we have many places in the run, and in those places we insert some loops. And our pumping is more or less like pumping a balloon. It happens in 2 dimensions. Something about our motivation. We wanted to get some geometric intuitions about vases before attacking some more difficult problems. And we think we succeeded with that because it turned out that our method can be really useful. For example, we may prove a short-run property using our tools. And currently, we work on adapting this technique to some even more ambitious problem, which is constructing semi-linear invariants for vases. So that concludes the intro. So now let's take a closer look at our pumping method. The core of our technique is a classification of runs that we provide. And using this classification, we prove that pumping is possible in two buses by showing separate pumping lemmas for each type of the runs that we consider. So we consider three types of runs: bounded ones, thin runs, and thick ones. So for now, I will skip their definition. Let me first show you the general structure of our method. So the intuition about those three types of runs is as follows. A bounded run is essentially a run that always stays in some area close to the origin of the coordinate system. It only uses configurations with numbers bounded by some constant m, depending on the size of the input bus. And bounded runs are not very interesting because they essentially behave like runs of finite automata. They have just finite space of configurations. On the other hand, thin and thick runs have infinite space of configurations. Thin runs look as follows. They are drawn on the 2D space, but they actually behave more like one-dimensional objects, while thick runs are truly two-dimensional. So for those three types of runs, we show some pumping lemmas. So for bounded ones, we just reuse the traditional pumping lemma for finite automata. It's very easy to show that you can pump bounded runs. For thin ones, the proof is a bit more involved, but it's also easy. We reuse standard techniques that are used with one-counter nets. We just use this fact that they are not truly two-dimensional. They only use one dimension at the time, some could say. Finally, the case of thick runs is the most interesting one. And for thick ones, we also prove a variant of pumping lemma, but I think it's the most interesting case. Those are not all the results that we need to prove that when we want to show that you may pump runs of two bus. The one last result that is needed is as follows. This is our theorem, that for any run pi of two bus, if it's not thin, then it's actually thick. So now let's take a look how, using all those lemmas and theorems, we may prove the pumping lemma for two buses. The structure of the proof is as follows. As usual, we are given some long run of the bus, and we want to show that we may pump it. So there are a couple of cases that we consider. So first of all, we ask the question, is the run bounded? And if it is, then we just reuse the standard techniques for finite automata. But if it's not, we ask one other question, is it thin? If it is, we use our lemma for pumping thin runs. And if it's not, by using our theorem, we infer that it's actually thick. So the second red arrow is the usage of our theorem that I showed you a minute ago. And in the thick case, we can also use the lemma for pumping thick runs. So all in all, we complete the proof. So that was our classification of runs. So now let's take a look at all those types of runs. I will now show you the definitions of those types, and then I will show you how you may pump those types of runs. As I already mentioned, bounded runs are not very interesting, so we omit them. And now we are left with two interesting cases, that is thin and thick runs. What is a thin run? We start with some constant m here. We consider a area here of points that are m close to the origin of our coordinate systems. Actually, we consider all possible integer vectors that use numbers smaller than m. For the sake of presentation, I only drawn 3 of them, but I would have to draw 1 vector per each point in this grid to be complete. All right, so we extend those vectors infinitely, and this way we form those red dotted lines. And now we consider neighborhoods of those lines, and the neighborhoods are again of size m. So the constant m is used 2 times here and here. And now, what is a thin run? It's very easy, no? A thin run is essentially any run that fits into the blue area here. For example, this one is thin. So now the question arises, how you can pump those thin runs. So we work under the assumption that the run is long and we want to pump it. So if the run is long, we may assume that it goes far into some regions of the blue belt when it's not, it's far from the other belts as well. So as you remember, the red dotted line is just produced by repeating the red vector many times. So using this fact, we may divide this blue area into a number of parallelograms like this. And now if we have a run like this, we observe what happens in different parallelograms. If the run is very long, then some repetition is bound to happen. Why is so? It's because those parallelograms only have finite number of points inside them. So a pair of configurations has to repeat. And when it does, we may pump this fragment in between the repetitions, or we may even delete it. So essentially, this is all about thin runs. This is how you can pump them. The definition of thick runs is a bit more involved, may seem a bit more involved, but actually it's especially tailored for our 2D pumping scheme. So we start with a run like this, and just for symmetry, we divide it into 2 parts. And now we consider those 2 parts independently. As before, we have some constant m here. And now we require this run to have some strictly positive vectors available in a close proximity to the origin of the coordinated system. What I mean by available? Well, essentially, in this point, there has to be a possibility to insert some loops starting from this state and ending in the same state here again. Sorry, I did not draw them. And the direction has to be positive on both coordinates. We also have some other vectors on the thick run as well, those red and green ones. And again, those vectors are realized by some loops. So we start from some state, we add some number of vectors, and we end in the same state that we started, but we moved to some other place. Now we don't have any requirements for those loops. It can also happen that those loops go below 0. We accept that. And why is so? Well, it's because we already have those strictly positive vectors here. And if we want to use this red loop here, we may just first make sure that it is safe to use it by going a bit to the positive section of the plane, and then we will eliminate this bad behavior here. So let's take a look at one of the parts of the run and analyze how inserting copies of those red vectors influences the endpoint here. So if you insert this first red vector many times, you actually move the endpoint along the same direction that the red vector points to. So I denote this with this. We have this direction available just because some of those some vector like this was available here before. And now if we take the other vector into account, it turns out that we may freely move into this red cone that I have just drawn here. The same applies to the second part of the run here. And now the important thing in the definition of thick run is that those two cones have to have non-empty intersection. So if a run, if we want to, so run is only considered thick if those cones have non-empty intersection. And now, what about pumping in this setting? It turns out that it is always possible. We just, using only the assumptions that I told you right now. So by analyzing some systems of inequalities, we can show that there is some solution. There is some combination of those red, green, and black vectors such that when we insert them into the run at once, we will produce a bigger and a valid run. So let's not get into the details here. I will just tell you that we analyze, first of all, some simpler system of equalities here. And we prove that it has an integer solution, non-negative integer solution, just because there is this non-empty intersection. And then we conclude that some other system also has a solution. And finally, the original system, we also prove that it has solution. And this system essentially encoded all the requirements for the run to satisfy, it encoded all the requirements for that run needs to satisfy to be valid. So if we have a solution here and we prove that there is always one, we may construct a bigger valid run. And now it looks as follows. We insert some number of the vectors from the first part of the run like this, and we move in the red cone on the picture. And we also insert some numbers of the vectors from the second part of the run, and we move somewhere in the green cone. And because of the requirements that we encoded in the system of inequalities, we end up in the same point. So now we just produced a bigger valid run. And now we may pump those yellow parts. That is, we may insert them many, many times, and we will get bigger and bigger valid runs. So this is how our definitions of thin and thick run work. And to remind you, we proved this. This is one of the most important theorems that we proved. It's not that straightforward because the definition of thin runs is not much related to the definition of thick runs. The thick runs are specially tailored for pumping, and thin runs, I don't know what to say about them, but the transition is not that straightforward, and it took us some number of pages to prove it in the paper. So all those results that I mentioned now complete the proof of our pumping lemma. So we may use the techniques that I just presented to prove the short run property, which says that if there exists a run, there also exists a short one in the TUVAs. So this is the third part of my presentation. The structure of the proof for the short run property is very similar to the structure of the proof of our pumping method, of our pumping lemma. It looks like this. So once again, we are given some long run here, and we ask if it's bounded. If it is, then again, the situation is very, very simple. If it's not, then then I have to tell you what happens. And if it's not thin, then it's thick, and we have some other reasoning here. So now let's take a brief look at those two. So you may have already figured out that the first case of thin runs is quite straightforward. As when you look at this picture again, well, essentially, if the run is very long, you may unpump it easily just by removing the orange area, and you will get a shorter run. So this is all we need to prove a short run property. The things are a bit more complicated for the thick runs, but it turns out that we also can do it. So when we have a thick run like this, we have those red vectors and green vectors and those black vectors here. We look at the numbers that appear in these vectors. Those are all small numbers, and we take product of them, and this is some constant m that we will use in a moment. Sorry, maybe not m, but n, some new constant. Now we break the run. How do we do that? Let's go back here again. We consider each part of the run individually, that is the parts between two vectors. And if they contain some loops that have the effect 0 modulo this constant n, then we just delete them from the run. So we get a very, very short run now, because now those lengths will be quite small. They will be roughly n or something. But of course, the run may break in the process. All right, for example, it may go below 0 here. So now we have to fix it. And it turns out that it's possible. Observe that we did not do anything with the initial short parts of the run before the black vectors appeared. So now we may freely use the black vectors, and we use them to fix the parts that could go below 0. So we write some other set of inequalities, and it turns out that it also has a solution. And when we have the solution, we can fix the run again. And now the run that we obtain is shorter. Maybe it's not shorter on the picture, but in general, we get something of predictable size. So this is how we can prove the short run property. Sorry, Wojtek, I forgot to control the time. How many minutes I have left?
I think you still have, so you have started something like 34. So you have used half an hour, so you still have 5 minutes of talk and then a few minutes for questions.
Very well then. All right, so that was short run property. And I showed you that our definitions of thin and thick runs work very well with it. So now let's take a look at the last point of my presentation. That is our motivation and our future work. So our main goal when we started to investigate those pumping methods was that we wanted to get some more intuitions about vases in general, because we wanted to be better suited to attack more difficult problems. And also, our original motivation was that we wanted to solve the regular separation problem for two vast languages. So, unfortunately, it did not work out. This regular separation is still open, but perhaps we will be considering it in the near future. I don't know, but for now, we work on something different. Oh, sorry, I did not update my slides. Okay, so now we are in the process of researching the existence of semilinear invariants for vases. And we are more or less sure that our techniques can be applied to get semilinear invariants in vases. And the question about inductive invariants is not yet resolved, but we have some intuitions that may work with this problem as well, but we need to verify that. And of course, this problem stays open, so I think that is quite interesting one. And I heard that Wojtek will tell you more about this problem in the open problem session after the break. So, in my presentation, I told you, I made a short introduction to the things we work with. And then I presented our pumping method, the short run property that can be proved using our method. And I discussed shortly the motivation. So let's sum up. This presentation was about 2D vector addition systems with states, which look like this. And problems for vases are very challenging in general. But we attacked something simpler for now, with a long-term goal of understanding the vases better to attack the more interesting problem in the future. We proved a new pumping method for two vases, and the core thing of this method was this classification of runs into thin and thick ones. And we proved that in both cases we may pump the runs. And then I told you that we may use our techniques to prove the short-run property in two vases. So that's it. That's all I had prepared for today. So thank you for your attention. And now maybe there are any questions. Are there any questions? So I finished now.
Do you see the chat? Thank you.
Okay, sorry.
I can read this if you want, but maybe you can.
No. I need to look at the chat because it was not visible for me. Something strange happened on my computer just now because I touched some cable. Do you still see my screen or something?
No, I just see you. I don't see your slides.
Okay. But I think that's not a problem then.
Okay. Do you see chat or should I read it?
I am opening the chat window now. All right. So what about 3D? Yes, so we are moderately optimistic about 3D because some of the techniques that we use here for pumping don't seem to generalize, but some other ones do. And I think we may use them to prove interesting results here. Actually, what we think we can do, and we are now writing the paper, is that we will be able to construct semi-linear invariants in vases of arbitrary dimensions. So not only 3D, but ND.
Maybe it's good to mention that actually we know we reprove the result, yeah? Like reproving result by Jerome, but maybe we can obtain some upper bounds on the size of separators.
I am a bit lost in the chat window. Are there any other questions? Dimitri is proposing invited talk at the next logic mentoring workshop. I don't know this workshop, but why not? Any other questions?
Okay, so if there are no other questions, so there is a question by Dmitry. The two final, it's not really a question, the two final slides were 3D, but this was rather about 3D. One more time. So you wanted to say the final slides something about 3D. Maybe you can tell this.
No, it's just about the technique. The pictures on those slides were rotated in the 3D.
I see. Okay, so thanks one more time, Radek, for a great talk.
Thank you for your attention as well.
And now we have a short break.